The universe is filled with wonders. Stars are born, galaxies collide, and planets dance around distant suns. But among all these wonders, nothing compares to the mystery and power of a black hole. A black hole is an object so dense, so extreme, that nothing can escape its gravity. Not even light. It is a cosmic trapdoor in the fabric of space and time, leading to a realm where our laws of physics break down. At the heart of every black hole lies a region called the singularity, hidden behind an invisible boundary known as the event horizon. Once something crosses that horizon, it can never return. But what really happens beyond the event horizon? What fate awaits matter, light, and even time itself when swallowed by a black hole? In this journey, we will explore the birth of black holes, their strange properties, and the theories that attempt to explain their hidden interiors. We will uncover what they mean for the future of physics, and why they may hold the keys to understanding the universe itself. Let us step closer to the edge and peer inside the most mysterious objects in the cosmos. A black hole is a region of space where gravity has become so strong that nothing can escape. The idea comes directly from Einstein's general theory of relativity, published in the year 1915. According to relativity, matter and energy bend the fabric of space and time. The more massive an object, the stronger the bend. A star like the Sun bends space enough to keep planets in orbit. But if enough mass is compressed into a small region, the curvature becomes infinite. That is a black hole. Black holes are born from the death of massive stars. When a star many times heavier than the Sun runs out of nuclear fuel, it can no longer fight against gravity. Its core collapses inward, and the outer layers explode in a supernova. What remains is a dense core that may shrink into a black hole. The size of a black hole is described by its event horizon. This is the point of no return. If the Earth were compressed into a black hole, its event horizon would be less than 2 centimeters wide. Imagine the entire planet crushed into a marble. That is the power of gravity at work. There are also supermassive black holes, millions or billions of times heavier than the Sun. These giants lurk at the centers of galaxies, including our own Milky Way. The black hole at the heart of our galaxy is called Sagittarius, a star. It has a mass equal to about 4 million suns. Black holes come in different sizes, but they share the same fundamental property. Once you cross their boundary, you are lost to the outside universe forever. Black holes cannot be seen directly. They emit no light, no color, and no signal that our eyes can detect. Yet scientists have developed ingenious ways to find them. One method is to look for their influence on nearby stars. When a star orbits an invisible companion, its path can reveal the presence of a black hole. By measuring the speed of the orbiting star, astronomers can calculate the hidden mass pulling on it. Another method is to observe X-rays. When a black hole pulls in gas from a nearby star, the gas spirals inward, forming an accretion disk. As the gas heats to millions of degrees, it shines with X-rays that we can detect with space telescopes. Gravitational waves provide a third method. These are ripples in space and time, predicted by Einstein, and first detected in the year 2015. When two black holes collide, they send out waves that spread across the universe. Instruments like LIGO in the United States and Virgo in Europe listen for these cosmic vibrations, confirming the existence of black holes with astonishing precision. The most dramatic evidence came in the year 2019, when the Event Horizon Telescope released the first ever image of a black hole's shadow. It showed the supermassive black hole in the galaxy M87, 55 million light-years away. The image revealed a glowing ring of gas surrounding a dark center, the silhouette of the event horizon. These techniques prove that black holes are real. They are no longer just equations on paper. They are cosmic giants that we can observe and study. The event horizon is one of the most mysterious concepts in science. It is not a physical surface, but an invisible boundary. Once something crosses it, there is no escape. To understand it, imagine falling toward a black hole. From far away, Time seems to pass normally. But as you approach the event horizon, gravity stretches time itself. To an outside observer, your fall appears to slow down. You would seem frozen at the edge, fading away as your light is stretched into longer and longer wavelengths. From your own perspective, however, you would continue to fall inward. You would cross the event horizon in seconds without noticing anything unusual. But once inside, no force in the universe could bring you back out. This strange effect, where time behaves differently depending on perspective, is a direct consequence of Einstein's relativity. It shows us that black holes are not only objects of immense gravity, but also laboratories for the nature of space and time itself. The event horizon marks the edge of knowledge. We can describe what happens outside it with confidence. But what happens inside remains hidden, shielded from view, locked away beyond the reach of observation. And that is where the greatest mysteries begin. Crossing the event horizon is like stepping into another realm. Inside, the rules of physics as we know them collapse. Gravity becomes irresistible. Space and time themselves are bent to their breaking point. According to general relativity, everything that falls into a black hole is drawn toward a single point at the very center. This point is called the singularity. It is a region where density becomes infinite, and where the known laws of physics can no longer describe reality. No one has ever seen a singularity. It is hidden behind the event horizon, cut off from the outside world. But the mathematics is clear. Relativity predicts that once matter crosses the horizon, it will inevitably be crushed into the singularity. What does that mean for matter and energy? Does it disappear? Does it remain encoded somehow in the black hole itself? This is one of the greatest debates in modern science. Some theories suggest that information is destroyed, but this conflicts with the rules of quantum mechanics. Others propose that information is preserved in subtle ways, perhaps encoded on the surface of the horizon itself, like a cosmic hologram. Inside the black hole, space and time switch roles. Moving toward the center becomes as inevitable as moving forward in time. You cannot resist it, because it is not a direction you can choose to avoid. It is simply the future. This is why black holes are more than cosmic traps. They are clues pointing to a deeper theory that unites relativity and quantum mechanics. To truly understand what happens inside, we must discover that theory. Black holes are not only mysterious, they are also violent. The gravity near their horizons is so intense that it can stretch and squeeze objects in ways that defy imagination. Scientists call this effect spaghettification. Imagine you are falling feet first toward a black hole. The gravity pulling on your feet is stronger than the gravity pulling on your head. This difference creates a stretching force along your body. At the same time, gravity squeezes you from the sides. The result is that you would be stretched into a thin, elongated shape, like a piece of spaghetti. The smaller the black hole, the stronger these tidal forces become near the event horizon. Falling into a stellar mass black hole, you would be torn apart long before reaching the center. In contrast, if you fell into a supermassive black hole, the horizon is so large that tidal forces at the edge are weaker. You might cross the horizon without immediate destruction, only to be stretched later as you approach the singularity. Spaghettification is not just a dramatic image, it is a vivid demonstration of how gravity behaves near extreme objects. It reminds us that black holes are not gentle mysteries. They are destructive engines that reshape matter and energy in the most brutal ways. And yet, from this destruction may come deeper insights into the nature of the universe. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery. He showed that black holes are not entirely black. They can emit faint radiation, now known as Hawking radiation. This idea comes from combining quantum mechanics with relativity. According to quantum theory, empty space is never truly empty. Pairs of particles and antiparticles constantly appear and vanish in a sea of quantum fluctuations. Near the event horizon of a black hole, one of these particles may fall inside while the other escapes. To an outside observer, it looks as if the black hole is radiating energy. Over time, this process slowly drains the black hole's mass. For large black holes, the effect is almost impossible to detect. A black hole with the mass of the Sun would take far longer than the current age of the universe to evaporate. But for very small black holes, Hawking radiation could cause them to vanish completely in a brilliant final burst of energy. Hawking's insight transformed our understanding of black holes. They are not eternal prisons, but objects that evolve and eventually disappear. This raises profound questions about the fate of information. If a black hole evaporates, what happens to the information about the matter it once consumed? Is it lost forever, or somehow preserved in the radiation? This puzzle is known as the black hole information paradox. Solving it could reveal the path to a deeper theory of physics, one that unites the quantum and the cosmic. Black holes are not just destructive forces. They also play a vital role in shaping the universe we see today. At the centers of galaxies, supermassive black holes grow by feeding on gas, dust, and even stars. As material falls in, it releases enormous amounts of energy, creating jets of particles that shoot out at nearly the speed of light. These jets can stretch for thousands of light years, lighting up entire galaxies. Paradoxically, while black holes consume matter, they also regulate star formation. By heating and blowing away gas, they prevent galaxies from forming too many stars too quickly. In this way, black holes act as cosmic engines that balance growth and stability. The Milky Way itself carries the mark of its central black hole, Sagittarius A star. Though mostly quiet today, in the past it likely erupted with bursts of energy that influenced the evolution of our galaxy. By studying these connections, astronomers have learned that the size of a galaxy's central black hole is linked to the size of the galaxy itself. This mysterious relationship suggests that black holes and galaxies grow together, locked in a cosmic dance. Without black holes, galaxies might look very different. They are not just monsters lurking in the dark. They are architects of cosmic structure, shaping the universe across billions of years. The greatest mystery of black holes is what lies beyond the event horizon. General relativity tells us that everything ends at the singularity. Quantum mechanics tells us that information cannot simply vanish. Reconciling these two ideas is one of the most urgent challenges in modern physics. Some theories propose that the information falling into a black hole is stored on its surface, encoded in the horizon itself like a cosmic hologram. Others suggest that information escapes slowly through subtle patterns in Hawking radiation. More speculative ideas imagine that black holes could be gateways. They might connect to other regions of space and time, or even to other universes entirely. These ideas remain unproven, but they show how black holes push science to its limits. What is certain is that black holes are more than astronomical objects. They are laboratories for the deepest questions about reality. They test our theories, expose their weaknesses, and hint at new physics beyond what we know today. Inside a black hole may lie the key to uniting relativity and quantum mechanics, the two great pillars of modern science. To look into a black hole is to look into the very foundation of the universe. Black holes are the most extreme objects in existence. They are born from dying stars, they sculpt galaxies, and they bend space and time to their will. They destroy, they create, and they challenge everything we think we know. We cannot see what lies inside them, but we can feel their presence across the cosmos. We can trace their influence in the dance of stars, in the glow of X-rays, and in the ripples of space itself. The question of what really happens beyond the event horizon remains unanswered. But every discovery brings us closer. From Einstein's equations to Hawking's revelations, from telescopes on Earth to observatories in space, the journey continues. As we gaze at the night sky, we know that somewhere out there, black holes are waiting. They are not only monsters, they are mysteries. And they may one day reveal the deepest truths of the universe. This is the story inside a black hole. And it is a story still being written.